Now sharing. Today we have to discuss with the 5-member heterocyclic rings, that is imidazoles. In imidazoles, the nitrogen, both the nitrogens are present. Two nitrogen present in the 5-member heterocyclic rings. The content of today's talk is we have to discuss with the properties, some syntheses or preparation reactions, along with some chemical reactions and medicinal use of the today's heterocyclic moiety, that is imidazoles. Here, this moiety is imidazole moiety. This moiety is we have to discuss today. Here the structure, you have to observe the structures. Here 1 and 3 positions, the nitrogen is present. One of the nitrogen having hydrogen atoms and another having the unshared electrons over it. This first position nitrogen is pyrrole-like nitrogens, whereas this nitrogen is 6-member nitrogens, that is pyridine-like moiety present in the structures, that is called as imidazole structures. The name itself indicates that imidazoles. Da means two, azoles means nitrogens. Two nitrogens in 5-member ring systems. All the atoms present in the 5-member heterocyclic rings are sp2 hybridized carbon atoms, where the first nitrogen having one hydrogen atoms, whereas third position nitrogen atom having the unshared electrons on present on nitrogen atoms. This is the fourth positions and this is a five positions. In second, third, fourth, fifth positions, these are the pi electrons. They are mutually shared with sidewise overlapping to make the double bonds in cyclic systems. If we consider the imidazoles having the 3 carbon atoms along with 2 nitrogen atoms as a heteroatom present in the ring. All the atoms are sp2 hybridized state. Due to the sp2 hybridized state, this structure is planar in nature, imidazoles, because the unhybridized p orbitals, they sharing its electron to make the sigma bonds as well as sidewise overlappings to form the pi bonds by overlapping of p orbital electrons and to make the pi bonds. Here in the imidazoles, the non-bonding electrons are 6. 3 from carbon atoms, 1 from nitrogens, and 2 lone pair electrons from nitrogens. So totally 6 electrons are involved in migration of double bonds. So as per the criteria of aromaticity, the particular compound is cyclic in nature, alternate single double bonds, carbon carbon single double bonds, like structures you have to observe. Here single bonds, double bonds, single bond, double bonds, alternate should be present in the structures, and it passes Hacker rules. Hacker rule means 4n plus 2 rule, pi, pi electron rule. While put n is equal to 1, then total electrons is 6. So as per the Huckel's rules, if put n is equal to 1, then the formation of 6 pi electrons. So these pi electrons are involved in the migration, delocalization of the pi electrons. Here on imidazoles, the 6 electrons are from 3 from carbon atoms, single carbon atoms. If you see here, these are the 3 from single carbon atoms, 1 from nitrogen means this one from nitrogens, and 2 unshared electrons, lone pair of electrons from this nitrogen, where the hydrogen is substituted. These electrons are involved in the migration of double bonds. So due to these natures, the imidazole is aromatic in natures. And another one is they available in the tautomeric forms by delocalization of these hydrogens from 1 to 3rd positions. If you see the tautomeric effect, here the 4 methyl substituted imidazoles you have to take as they undergo tautomeric due to the resonance delocalization of pi electrons. They shifting the hydrogen from one position to 3rd positions and to make the 2 methyl imidazole available. 5 methyl imidazoles. Why 5? 1, 2, 3, 4, 5. So there is a formation of 4 or 5 methyl imidazole is a substituted product. Due to the tautomeric effect, it will form the tautomeric structures. And hydrogen bondings is involved, intermolecular hydrogen bondings. Hydrogen of one of the imidazole. This hydrogen from this imidazole rings, they bind with the nitrogen of the other imidazoles, those having lone pair of electron present on 3rd positions. 3rd position nitrogens bind with or bond with hydrogen of first positions. They are partially bind with the hydrogen of first positions present on imidazole rings. These are the some properties related with the imidazoles: aromatic properties, tautomeric properties, hydrogen bonding ability of hydrogens, which is present on first positions. Now we have to move with the preparation of the imidazoles or synthesis. Both the words you have to use, either preparation or either synthesis of imidazole. First synthesis of imidazole is Radix-Squeezy synthesis. For Radix-Squeezy synthesis, the starting material is dicarbonyl compounds. These are dicarbonyl compounds. They react with the ammonia to form the diamines. These are the intermediate which is used for the preparation of imidazoles. Followed by they react with the aldehydes, substituted aldehydes, and to make the cyclizations. Followed by condensation and to make the substituted imidazoles. That is 2,4,5 substituted imidazole was formed. First step is formation of diamines. After formation of diamines, they undergo cyclization in presence of aldehyde and to make the necessary cyclized product, that is imidazole containing substituted components. In this way, you have to prepare the synthesis from dicarbonyl compounds. Second method for the preparation of imidazoles from alpha halocarbonyl compound. This is a carbonyl compound. Adjacent to carbonyl compound, this is alpha carbon atoms, where the alpha carbon atom containing halogen, that compounds are called as alpha haloketones. Alpha haloketones react with the amidins. This is the structure of amidins. Substituted amidins to form the substituted imidazoles. There is a liberation of bromine ions. There is substitutions and liberation of these hydrogens and oxygen of alpha halocarbon atoms. Loss of one water molecules along with bromine ions and to make the necessary substituted imidazoles. Whereas another reaction, instead of alpha haloketones, alpha hydroxy ketones also undergo react with the amides. There is a, instead of bromine ions, there is a loss of two water molecules, OH and hydrogen from this amides, and oxygens and H2 molecules from this amides, and to make the necessary finalized substituted imidazoles. In this way, you have to prepare the imidazoles from alpha haloketones or alpha hydroxy ketones. That is acetylene, which treated with the amides to form the imidazoles by loss of water molecules. Another is from dehydrogenation of imidazolines. This is the structure of imidazoles. Nothing but there is a reduced form of imidazoles. These undergo reduction. These undergo dehydrogenations. There is a loss of two hydrogens. Hydrogen from this side and this side. Loss of one molecule of hydrogens, and to make the substituted product. For the preparation of imidazolines, they react with the diamino ethanes, react with the cyanides, or called as alkyl nitrides. With loss of one molecule of ammonia, there is formation of imidazolines. These imidazolines undergo dehydrogenations in presence of barium magnates, and to form the two substituted imidazole as a final product of dehydrogenation of imidazolines. These three preparation reactions you have mentioned. There are n numbers of preparation reactions you have to observe related with the any heterocyclic compounds. But here we have to take the important ones for the preparation of imidazoles. First is Radisky imidazole synthesis from dicarbonyl react with the ammonia, formation of diamines followed by aldehyde reactions to form the cyclized product, whereas from alpha halocarbonyl compounds or alpha hydroxycarbonyl compound react with amidines by loss of water molecules to make the substituted imidazoles. And whereas another method for the preparation of imidazoles from imidazoles, they react with the barium magnet by dehydrogenation, loss of two hydrogen molecules from imidazolines, making of double bonds in between two carbon atoms, and to make the two substituted imidazole as a final product. Now we have to move with the chemical reactions of imidazole. First property or first reaction is basic property of the imidazoles. That is protonations. The imidazole accept the protons and act as a base in the reactions. Here, this is a structure of imidazoles undergo protonations. These protons added into the lone pair containing nitrogen atoms, and this nitrogen acquires positive charge after protonations, and to make the imidazoline cations. These are tautomeric forms or resonance forms. There is a delocalization of this positive charge due to the presence of this delocalization of pi electrons over it, and this charge transfer over nitrogen atoms, and to make the imidazoline cations. These cations act as a, here imidazole accept the proton and act as a base due to the basic property of imidazoles. There's a protonation. First, electrophilic addition to nitrogens. There is an addition of electrophiles on nitrogen atoms. This nitrogen having lone pair of electrons involved in the protonations because of the basic property of imidazoles. Now, another reactions, electrophilic addition to nitrogens. That is N-alkylations. First is protonations, second is N-alkylations. What is meant by N-alkylations? N means nitrogens. Alkyl substitution on nitrogen of imidazoles. Where substitutions, where the unshared electrons present on particular nitrogen atoms out of these two, where the alkylation was carried out. For alkylation, alkyl halides are used in presence of acid. Acid act as a catalyst for alkylation reactions. These methyl substitutions are substituted on this lone shared lone shared unpaired electrons containing nitrogen atoms, and to make the intermediate, that is positive charge nitrogen containing imidazolium salt, that is N-methyl imidazolium salts. The tautomeric form is light and shifting of positive charge or first nitrogens and hydrogen and delocalization of the pi electrons. Again, there is a possibility of removal of hydrogen from this intermediate N-methyl imidazole salts because imidazole act as a base, removes the proton. Which protons? By protonations. And again, alkyl halides are attacked to the second nitrogens and to make the another salt, that is dimethyl salt. Which type of dimethyl? N1 and 3 dimethyl imidazoline salt was formed. This type of reaction is called as N-alkylation reactions. In the first step, if imidazoles without unsubstituted imidazoles, they undergo alkylations, alkyl halide in presence of acids to form the intermediate by delocalization of the pi electrons present to the positive charge, delocalization of positive charge from third carbon nitrogen atom to first, followed by deprotonation, loss of this nitrogen protons, and to make the unshared electron containing nitrogens. Again, they undergo alkylations and to form N1, N3 dimethyl imidazolium salt formations. Which type of salt? Iodide salt. These are the electrophilic addition to the nitrogens. Nitrogen already having the electron density where the electrophiles are easily added. Here, electrophilic substitution to the carbons. Apart from nitrogen, carbon. Which here there are three carbon atoms. There is a second positions, one carbon atom, fourth and fifth positions. If you can say with the imidazoles. There is. In electrophilic substitution to the carbon atom, C2 substitution is not favorable because at C2 positions it forms highly unstable N plus ion containing intermediate because if electrophile substituted, this moiety is unstable ones. So this is the unfavorable conditions for electrophilic substitutions. Whereas fourth and fifth position gives the more stable resonance structure with this imidazole. So fourth and fifth position is a more favorable electrophilic substitution positions to carbon atom instead of C2 positions. So now we have to move with the electrophilic substitution reaction. First is nitrations. In presence of nitric acid, nitration is carried out. At fourth position, there is substitution of nitrogens or 5-nitro imidazoles due to the delocalization of these protons from one position to the third positions. Due to the tautomeric effect, there is formation either 4 or 5 nitroimidazoles. Similarly, sulfonation was carried out in presence of sulfonic acid. Sulfuric acids, imidazoles undergo sulfuric acids. There is a formation of imidazoles 4 or 5 sulfonic acid substitution. There is a SO3 substitutions, fourth or five substitutions. Due to the tautomeric effect, 4 and 5 substituted sulfonyl substituted imidazole was formed. Whereas another electrophilic substitution reaction, that is halogenations. For halogenations, your bromine is used, bromination reactions. There is formation of 4 and 5 substituted as well as second substituted. 2, 4 and 5 substituted tribromo imidazole formations, followed by react with the sodium sulfide, form the 4 substituted 1H imidazole is a major product of halogenation. This type of product was formed with electrophilic substitution to carbonate. Now move with the another reactions. Imidazole catalyze ester hydrolysis. The ester hydrolysis in presence of imidazole was carried out. This type of reactions here is the ester. Esters undergo hydrolysis in presence of imidazoles and to form the protonated imidazole formations, proton ions formations. There is a substitution of this hydroxy group towards esteric forms, whereas these protons attack on nitrogens of imidazoles and to make the substituted proton substitution products. Whereas if you go with the esters, there is addition of alkoxy groups, removal of alkoxy group from esters.